Hello, I hope you are doing well. And now we start to see the diagnostic horizons of WRB. The diagnostic horizons in the WRB can be grouped in some specific clusters according with the topology or according with the process that create these diagnostic horizons. And the first group that we start to discuss is the human affected horizons, horizons that are at the surface or subsurface and are deeply influenced or created by humans. The first diagnostic horizon that we need to pay attention is the anthracic horizon. The anthracic horizon is, as the name says, anthra, so it's human made, and aquic, aqua, so water. So it's a horizon where humans induced flooding, so, especially in Asia, in rice fields, people they induce the flooding of soils, and because of this, these horizons and these sections present some specific features. Okay, the Antarctic horizon is a surface horizon formed by cultivation of soil in wet conditions, and as I said, this flooded conditions should be induced by humans. So regular or natural flooding cannot create the Antarctic horizon. The Antarctic horizon, as I said, it's quite common in Asia, but of course, now we can classify Antarctic horizons everywhere since we have flooding and cultivation induced by humans. The Antarctic horizon is this dark horizon that you can see at soil surface, and at same time, this dark color is also combined with redoxymorphic features, which express this flooding, this water high saturation condition. The characteristics to classify an anthracic horizon is that this surface horizon consists of mineral material, and I would not say now the content of organic carbon, or I can say it's quite higher than the soil taxonomy. It's quite higher than the Brazilian system. WRB consider to identify an organic layer with a content of 20% to zero. So any section of soil with 20% or more than 20% is classified or identified as an organic section. So all the other sections are considered mineral material, and the Antarctic horizon it's one of these examples. So the content of organic carbon to identify the Antarctic horizon should be lower than 20%. Okay? And much more than this, we need to find a pudlet layer. And what is this pudlet layer? It's a layer without structure, which the structure was destroyed by human and slash or animals action. Okay, so a surface section with absence of structure or pads or a weak development of pads should present in 80% or more of the exposed area. A hue of 7.5 YR or yellower than this and low velo and low chroma, so dark colors, or a hue that's JY, B, or PG that express gray colors. A mix of green and yellow, blue or blue and green, and a value equal or below 4. So again, dark colors. And the anthracic horizon also should be above a blue pen. So below the anthracic horizon, I need to find a layer or a section that avoids water migration, that avoids water percolation, and because of this, create this fluid conditions. This fluid pan should be below this pudlet layer or this layer or section without structure, and the blue pen should present a platy structure or a massive structure in at least 25% of its volume, expressing a very intense consolidation of a horizon because human action at the surface. And this blue pen also should present a bulk density higher, at least 10% more than the surface layer. And the anthracic horizon also should present oxymorphic features in at least 5% of the area, especially in biopores or pores expressing concentration of iron in some specific zones where is water is absent, and especially oxygen is abundant, expressing that we have some specific conditions that induce iron oxidation. Okay, we will see in the next slides and especially in the next classes that WB describes very well the occurrence and especially the spatial distribution of oxymorphic and redoxymorphic features. When we find oxymorphic features expressing iron and or manganese concentration in biopores, we are saying that our soil and at least that section has some problems to induce water penetration or water drainage through this specific horizon or all the soil. So when we find models, plintite, any kind of feature that express iron and or manganese in biopores and inside the aggregates, we are saying that the water that came from precipitation or water that came from the surface and starts to penetrate through the soil voids, this water penetrates very, very slowly and cannot be drained through all the soil. So this water induce some reduxomorphic features, and then because of this, some zones gets dark colors, and inside biopores where the organisms induce or add the presence of oxygen, we have iron oxidation and then formation of models and plintite very close to biopores or inside the aggregates. We'll talk more about this in the next slides and show some pictures. Don't worry about this, okay? Oh, and we also have in this oxymorphic features higher hue and higher chroma than the surrounding material. Of course, if we are saying that we have concentration of iron, we need to register higher hue and higher chroma in these areas. And of course, we need to consider a thickness of at least 15 centimeters because all the diagnostic horizons have specific thickness that should be followed as the rest or as the others diagnostic criteria. We also have the Arctic horizon, and the Arctic horizon express addition of organic carbon and fertilizers by humans. So in some soils with a very low fertility, humans can induce the increase of fertility, adding soil organic carbon and fertilizers, then create the Arctic horizon. The Arctic horizon is a horizon with dark colors, high base saturation, high content of phosphorus and carbon, and high biological activity. The Arctic horizon is quite common in Europe, but you can think on it in several places that humans induce or increase soil fertility. The diagnostic criteria to identify the Arctic horizon is that we need to find dark colors, so low velo and low chroma, a content of soil organic carbon equal or higher than 1%, a content of phosphorus extracted by malleage tree equal or higher than 120 milligrams per kilogram of soil in the first 20 centimeters, a base saturation that's equal or higher than 50%. And here I need to mention something that's quite important in WRB. In soil taxonomy in the Brazilian system, it's quite common to say that a high base saturation express euteric and low base saturation express district properties and district characteristics in the soils. So again, in soil taxonomy and Brazilian system, it's quite common to say that if the soil has, for example, 80% of base saturation, this soil is euteric. Okay, in WRB, this is not true. In WRB, base saturation, it's one of the features, it's one of the properties that we describe and use to classify and identify the diagnostic horizons. But eutric and district are other features, other soil properties that we also describe and we use to classify the soils. Iltric and district and WRB, they are related to the content of bases and the content of aluminum. If the soil has a higher content of bases, for example, calcium, magnesium, sodium, potassium, higher than the content of aluminum, so this soil is euteric. On the other hand, if you have a higher content of aluminum, a higher than the summed content of calcium, magnesium, potassium, and sodium, you have a district soil or at least a district horizon. Okay. So again, pay attention, be worried that base saturation, electric and district properties or expressions, they are different in WRB. Okay, so keep this in your mind. And of course, we need to talk about this a lot of times, and I will try to at least once per class highlight this because this is really important. This is a big deal in WRB, and it's a big difference between soil taxonomy and WRB. But it's quite important to keep this because a lot of people make some mistakes and mix WRB with soil taxonomy in this specific case. Okay. Um, Also, for the Arctic horizon, not only the high base saturation, but also expressions or features that express soil animal activity, like pores created by termites, by wormholes, and coprolites and other traces, any kind of feature that express or could express animal activity or bioturbation, it's important to describe and classify the Arctic horizon. And also a thickness equal or higher than 20 centimeters. Okay, this is important to identify the Arctic horizon. We also have another horizon that it's also formed by humans, is the hydraulic horizon. And hydraulic horizon is a subsurface horizon that's formed below the anthropic horizon. So again, the anthropic horizon is that surface horizon created by humans in cultivated and flooded sites, but at subsurface, you also can find a horizon that has a high built density, remember? And it was also created by humans. And this high book density horizon also express reducimorphic features. So in WRB, it's the only system that considers that humans also create subsurface horizons. In this case, this hydraulic horizon. The hydraulic horizon has some diagnostic criteria. First of all, we need to be below the anthropic horizon, of course. Second, we need to find reducimorphic or reduced morphic features, features that express reduction, okay? Features that express destruction of iron oxides. And we need to present, in this case, a high value equal or higher than 4, and a low chroma equal or below 2, both moist and close to biopore walls. So, for example, I need to see something like this. You can see here my fingers, and I'm pressing a pad, and in this aggregate we can see this yellow color very easily, but in the middle of it we have a biopore. In this case, this pore was created by roots, and in the middle of this pore we can see a gray color, or a color that express reduction or iron oxides destruction. Okay, so in the middle of this biopore we can see some expression of reducimorphic features or reducimorphic features, features that express reduction. The other diagnostic criteria to identify the hydraulic horizon is also find at least 15% of area with oxymorphic features, so mottled and plintites. And these oxymorphic features, they should be inside the soil aggregates and present a higher hue and a higher chroma than the surrounding material, or I should identify in at least 15% of the area reduct oxymorphic features in the biopores. So it's the opposite of the last picture that I show you. Now I need to see inside the pads or around close to the biopores oxymorphic features, features that express iron oxidation. I will show you some pictures. In this case, you can see this pad again, my fingers here, so you can see that this is a little pad, but it's quite close to my camera. Okay, so it's why this is really big. And you can see this gray color in the pad, but close to the pores, close to the spores that were created by animals and roots, I can see a redder color. I can see higher chroma expressing iron concentration and iron oxide formation around pores. They form here, the iron oxides are created, are formed here because I have a lot of oxygen. Oxygen induce formation of iron oxides again in this depleted iron environment. Here you can see it in the soil profile. So a lot of voids, and around the voids, I can see this redder color. Okay, but the soil has a gray, a strong gray color. So the horizon, it's quite poor in iron, but around the biopores, the pores formed by animals and roots, I can see some iron concentration. Here is the same. Again, I can see this gray color, but close those voids created by roots or animals, I can see oxymorphic features, features that express concentration and precipitation of iron oxides. Here again, I can see this oxymorphic features or oxy features, features that express concentration of iron oxides inside aggregates. Okay. Or I also can dose or measure the content of iron that can be extracted by deutonite, and this content should be equal or higher than 1.5 times, and manganese should be equal or higher than 3 times than the average of this layer over this hydraulic horizon, or the anthracic horizon should present a lower content of iron and manganese that could be extracted by deutonite. So the total content of iron in manganese and the hydraulic horizon should be higher than the surface horizon. And of course, hydraulic horizon also should present a minimum thickness. In this case, it is 10 centimeters. We also can find a egracic horizon. The egracic horizon is a horizon formed by irrigation. So egracic horizon is a surface horizon that is straight related to irrigation, and it is formed in areas that use poor quality water to irrigate soils, especially water that has a high content of silt and fine sand. If we have an intense and long irrigation, we can add material at the surface, at the soil surface, and sometimes create a thick horizon as this one. Okay, so this picture, it's not mine. I never saw a irregular horizon at the surf at in my life at the surface at the field, but you can see here in this picture that I extract from one article that we have here the past soil surface with a darker color, and all this section with more than 20 centimeters is the Ihagric horizon, is a horizon that buried a past surface horizon because add material from irrigation. The poor quality water brings silt and fine sand, and these particles buried was concentrated or accumulated at the surface and buried past surface horizon. Okay, it's quite interesting, right? Think that you need to use a very water with a very high content of solid particles in this water to add this material, and this irrigation should take a long time to create an Y horizon. And the Y horizon should register, of course, soil structure. So I need to see at least a little of pads or aggregates. And the clay content should be equal or higher than 10% in a relative way and 3% in an absolute way than this buried horizon. So you need to register a higher clay content in this geographic horizon. Okay. And also I can, in an alternative way, find a higher fine clay content in this geographic horizon. So both cases are okay. The hierarchy horizon also should register some differences in sand content or silt content or clay content or carbonate content that should be lower than 20% or in a relative way or 4% in an absolute way between subhorizons. So the content of sand, silt, clay, or carbonates among all the subhorizons that compose the geographic horizon should be very low, should be very homogeneous, and this specific surface horizon should present a soil organic carbon content equal or higher than 0.3%. It's a very low organic carbon content, but it should be followed. Okay. And if you have more than one subhorizon, so I can identify one, two, or three subhorizons that compose the geographic horizon. So the average soil organic carbon content should be equal or higher than 0.5. Okay. I should see some, oh, I should see at least 25% of area of exposed area with evidence of animal activity of bioturbation like biopores, coprolites, and others, kind of evidence that express animal activity. I need to register any evidence in the field that it had suffered land surface raised that has been raised. Okay. And it's quite common to see this in the field because you can see that, for example, the areas that are cultivated, they register higher altitudes, could be some centimeters, could be 1 meter, 2 meter, or even higher than this. This is enough to register that one specific land surface was raised in the past by human action. And again, we have some minimal thickness. In this case, 20 centimeters to 0. We have the pelagic horizon, and the pelagic horizon, it's quite similar to the Pelagian pattern that we register in soil taxonomy. The pelagic pattern, as the Pelagian, like the Pelagian pattern, is a horizon formed by addition of sod and organic carbon by humans in very low fertility soils. So when people try to cultivate in some specific soils, especially podzols, spodosols, the very low fertility avoid a high productivity. So people start to excavate organic matter from the forest and bring organic material and incorporate it and mix with the soil, especially using some kind of materials. And this kind of mix create the pelagic horizon. Okay, the pelagic horizon express a dark color, a low base saturation, and acidic pH, and median, at least a median organic carbon content because the addition of organic materials from the surrounding areas. The diagnostic criteria to identify a pelagic pattern is that, first of all, it could register a sandy or loamy texture and register any kind of artifacts or evidence of human action. It should register a content of phosphorus that is equal or higher than 100 milligrams per kilogram of soil in the first 20 centimeters. Of course, we need to think humans bring material to increase soil fertility. So the soil fertility should be high, at least the phosphorus content should be high. Okay. As I said, we need to see any kind of evidence of human action. For example, plug layer or any kind of mark like spat mark or hood marks that express the mixing of soil. It should register a dark color, so of course a low value and a low chroma, a content of soil organic carbon that's equal or higher than 0.6%. The base saturation is low because people add only organic matter, and this create a low base saturation horizon. Okay, so in this case, the content of some of bases split by the CEC and multiplied by 100%, it should be lower than 50%. So the pelagic horizon also should evidence any kind of land surface raised. So again, I should register in the field any feature that express land surface raising, and of course a thickness, a minimum thickness that in this case it's equal or higher than 20 centimeters. We also have another horizon that's formed by humans, and this specific horizon it's a quite of special horizon in Brazil because the Pratic horizon was created because because the specific Brazilian soil that of course occurs in other areas, especially in South America, but it was discovered and first described in Brazil, and it is called Amazon Dark Earth. And because of name, you can at least have an idea that you can find the soils in Amazon. Yes, you are true. They are pre-Columbian soils formed by indigenous that add, mix, burn, created soils because they have a lot of different activities in these areas. They could bury and burn people, some families, or someone that was really important between them, or they can just bury trash, or they can just bury trash to create highlands so they can see the surrounding and protect them against other kind of tribes or other kind of um, enemies that could be close to that area. And in this Amazon dark earths, in the Pratic horizon, you can see a lot of potsherd, ceramic, bones, seed, charcoal, ash, and of course, I'm describing a lot of materials that are calcium, magnesium, phosphorus and carbon rich. And because of this, you have this dark color and a high fertility. They are horizons that register a very high fertility, okay? Because we add a lot of components that are rich in some nutrients that are really important to plants and animals. So here in this picture, you can see this yellow and red spots that are some ceramic fragments that are being dissolved by the very wet climate condition. And you also can see some charcoal fragments here and here. Here you can see a ceramic fragment, a pot share that was buried by humans. Another example of ceramic and pot share here. Another example. And okay, here you also can see some shells that and bones that were added by humans. So here you already saw this picture is a pratic horizon. It's a horizon produced by humans and by a deep, in, intense addition of organic rich materials. Okay, this specific horizon, as I said, it's quite common in some specific regions in Brazil and other areas in the South America. To identify and classify a pratic horizon, what I need to check? First, the color. Of course, pratic means black in Portuguese. So the pratic horizon should register low value and low chroma. The content of organic carbon should be equal or higher than 0.6%. The exchangeable calcium plus exchangeable magnesium should be equal or higher than 1 centimole charge per kilogram of fine earth. The content of phosphorus should be equal or higher than 100 milligrams of phosphorus per kilogram of soil extracted by malech tree. We also need to find some at least 1% of area covered by black carbon that are charcoal or ash, or at least 0.3% of some molecules or some chemical composition related to black carbon. So I can measure the content of an inorganic carbon, and in this case the inorganic carbon should not be related to carbonates. Okay, if I measure at least 0.3% of carbon, inorganic carbon, that's not related to carbonate, it's okay, I can classify it as a pratic horizon. Or I can also measure, I can also calculate a ratio between the inorganic carbon and total organic carbon. So inorganic carbon, that again, it's not related to carbonates. Okay, so if the content of carbon that's related to ash or charcoal, and I can measure it with the total organic carbon in some equipments, and this ratio it's equal or higher than 0.15. So okay, it helps to identify it as a pratic horizon. And of course, also need to consider a minimum thickness. In this case, 20 centimeters. And in this specific case, we consider that one or more layers that when combined, they present a thickness of 20 centimeters. So if I have more than one layer, the combined thickness of them should be equal or higher than 20 centimeters. And we have the last horizon that is formed by humans is the thermic horizon. The thermic horizon is a kind of European, especially European horizon, but of course, we also can see it in South America. It is a horizon formed by humans when these humans try to bring material from one area to another area, not only to increase the soil fertility, but now especially to create flat surfaces. So they try to create a flat surface so it's easier to cultivate. So you can see in this picture a lot of levels, and these levels, they are really flat. They were created by humans so people could cultivate in these flat surfaces, and this cultivation is quite easier because of the flat surface. Okay, the addition of material is basically material that it's bring it from the surrounding areas, and they bury some horizons and they bury some layers trying to create some flat surfaces. And because of this, because of the addition of material from the surrounding, especially mineral material from the surrounding, they create high base saturation horizons, high pH horizons, and a high fertility soils too. So this is one of examples that you can see very, very easily here, where I show my pointer. In this specific part, the soil was formed in situ, and all this material above was excavated, carried, and deposited here to create this flat surface. So all this material here was bring f- from another area and was deposited here above the in situ soil. They register high base saturation and high pH, expressing a high fertility. And you can see that the color is not too dark. It's something more a mineral material with a flat surface. So again, to identify the steric horizon, you should register any evidence that express the addition of a material from the surroundings. You can see some artifacts, materials that express human action. You should register a minimum content of organic matter that should be equal or higher than 0.6%. You should register a base saturation that's equal or higher than 50%. You should register any evidence of land surface raising. For example, the creating of these flat surfaces and of minimum thickness that is, in this case, 20 centimeters.